Let's start today's class. So, in the previous class, we learned about the statically scheduled pipeline architecture. So, actually, this pipeline architecture is very similar to the simple 5-stage pipeline architecture we learned in undergraduate computer architecture course. So, which means that the instructions are fetched in order. Also, instructions are decoded. Instructions are decoded in order, and then also another feature of this statically scheduled pipeline architecture is that instructions are executed in order. So, in order means that we know that our assembly instructions are executed from top to bottom. Actually, these instructions are executed in the processor with the same order. So, but we learned that because of data dependencies, the performance of the statically pipelined architecture is degraded. So, which means that in this pipelined architecture, we need to exploit instruction level parallelism. So, which means that we require many instructions which can be executed in the processor. But if not, and if we cannot find any instructions which can be executed in the processor, then clock cycles are wasted. So the performance is degraded. So that's the problem of statically scheduled pipeline architecture. So I simply call it static pipeline architecture. So usually in the very simple 5-stage pipeline architecture, you need to consider the data hazard. Actually, we don't need to consider the structural hazard because actually the instructions are executed in order. So we don't need to consider about the structural hazard, but we need to consider the low hazard. So it's a data hazard. So actually data dependencies. The hazard means that the clock cycles are wasted, but we can find data dependencies frequently in our code, and it's obviously true. So you need to consider low hazard. Also, actually, control hazards are also critical for the performance of the static pipeline architecture. So, actually, in the undergraduate course, we learned about how to reduce some data hazard, and then we also learned how to reduce control hazard in the static pipeline architecture. So we can reduce the data hazard with the data forwarding. So if we cannot reduce the data hazard, if we cannot avoid the data hazard, then we need to store pipelines. Okay. And also, also we learned about some different static pipeline architecture, such as okay, like this out of order execution completion. So actually, we already know that the integer units are much simpler than the floating point units. So if the hardware structure is complex, then it will take longer time. And then in the pipeline architecture, the hardware structure is complex, and it will take more cycles. So which means that actually we assume that integer unit, the execution of the instruction is completed within one cycle. But it's not true for the floating point unit because the floating point data is very complex. So it will take more cycles. So in this example, we assume that the floating point unit takes 5 cycles, which means in the simple 5-stage pipeline architecture, the instruction is completed in order. Okay, and it's very good because you don't need to consider about the order of the completion of instructions, but it's not true for this pipeline architecture. And because of this floating point unit, and it is the number time, so which means that the completion is not in order. So we need to consider some additional aspect of the data dependencies in this pipeline architecture. So which means that we need to consider the additional data hazard called the WOW hazard, so WAW hazard. So actually in this case, in consider only WAW WOW hazard. Okay. Okay. Also, precise and exception is another issue in this out of order completion processor, because actually we assume that the processor needs to support the precise exceptions, but which means that the exceptions, actually the exceptions are handled when the when an instruction is in the right backstage. But problem is that, this is the out of order completion processor, so required cycles until the right backstage is different. So it's not easy to support the precise exceptions. But we cannot just the pipeline architecture like this. So it's the force in order completion. And then also we can consider the superscalar CPU, because so in this process architecture, we can find that there are multiple processing engines, such as the integer engines and then floating point engines. So which means that if there are multiple execution engines, which means multiple instructions can be executed concurrently. So by exploiting this feature, that we can fetch multiple instructions, like the integer floating point instruction pair in this superscalar CPU. So which means that integer instructions and the floating point instructions can be executed in parallel. Okay? But also another issue. So another issue is that, so in order to use this superscalar CPU efficiently, then this pair, the integer and the floating point instruction pair, should be found in every code. But it's not easy to find this integer and floating point instruction pair in our code arrays. So it's some another performance degradation issue in the superscalar CPU. Okay. So we learned about the static branch prediction, and then this compiler techniques. So actually, in the statically scheduled pipeline architecture, the hardware cannot reorder the execution of instructions. So which means that in order to increase the performance of this processor, then a compiler needs to reorganize the order of instructions to increase the performance. So which means why? If we just use some not optimized code, so it means and then we can find any data dependencies in this code, like and then data dependencies cause load hazard. And then another problem is that if we use the floating point arithmetic instructions, then it will take more cycles. And then if the following instructions require the result from the former floating point instructions, then we need to wait until the results are ready in the processor. And then that's the waste of cycles. So performance can be degraded. So in order to avoid this case, the compiler needs to reorder reorganize the order of instructions. In this example, we can find that by reordering the instruction order, then we can increase the performance. And it's a huge improvement actually, the 25%. Okay, just 25% performance is improved about the 25%, but it is a very actually it's a rare case. So it means that I explained about the local optimization and global optimization by compilers. The local optimization means that compilers can reorganize the order of instructions inside of base block. So it is because in the base block, if the first instruction of the base block is executed, then we can guarantee that instructions are executed in order until the last instruction of the base block. So actually, it's very easy. It's if the compiler knows the hardware architecture, process architecture, then it's very easy to reorganize the order of instructions inside of base block. But also, I explained that actually the typical size of the basic block is about 4.5, which means that we can find only 4 or 5 instructions normally usually. So it's the average number. So which means that we can find only 4 and 5 instructions inside of a base block. But so if there are very small number of instructions, then it's very hard to find the appropriate instructions in the base block. So which means that we need to increase the number of instructions inside of the base block. Okay. And then so another compiling technique to improve the performance is loop unrolling. Okay. So iteration loops are frequently used in our code, and it's true. Okay. So we frequently use the code similar to this code. So we frequently use the for loop or while loop in our code, because that's the benefit of programming. So without this, our program, we can repeatedly execute the same kernel or same instructions inside of our code. So this observation, iteration loops are frequently found, and then the compilers can also analyze the number of iterations. We can just estimate. So it's 100% correct, but we can, if we see that this code, then we can easily estimate that this loop will be executed 100 times, repeated 100 times. So if compilers can know the number of iterations, then we can apply loop unrolling. The benefit of the loop unrolling is that the number of instructions inside of a base block increases. Okay, so which means that we can find appropriate instructions which can be reorganized inside of this new base block. So that is the loop unrolling. But then, what is the issue of the loop unrolling? So loop unrolling is very good. What are the issues of this loop unrolling? So, sorry. Number of available registers. Okay. So, the number of registers are defined in instruction set architecture. Actually, we can call it as the architectural registers. So, actually, number of architectural registers are fixed, which means that compilers need to select the available registers from among these architectural registers. So, for example, in the RISC-V, we have 32 general purpose. We can use the 32 general purpose registers. Also, the RISC-V can use the 32 floating point registers. So which means that the number of registers is just 32. So we need to select the appropriate registers from these architectural registers. But if we apply loop unrolling, so if the basic block size is very small, so instructions, the number of instructions are very small, then these instructions will use a small number of registers. But so if the loop is unrolled, then we need to change the registers for the another loop. So and the instructions in another loop need to consume more registers. So which means that compiler need to assign more registers in the unrolled loop. So which means compiler needs to find the available registers. And then why is this? Why does it matter? So if a compiler cannot find available registers, then the data should be stored in the stack. So then the stack is in main memory. So we need to use the load and store instructions to organize the to control the data transfers between registers and the stack. So if we use the load and store instructions frequently, the performance can be also degraded. That is another problem. The performance can be degraded. So that is the issue of the loop unrolling. Okay. And then also we can apply the loop unrolling for the superscalar processor. The superscalar processor means that the integer. So we can execute the integer and floating point instruction pair. Sorry. So we can execute the integer and floating point instruction pair in the superscalar processor. Then we can apply some loop unrolling for this superscalar processor. So and then, but the problem is that as you can see, this a fraction of the instruction, integer instructions and the floating point instructions is not 50-50. Okay. So as you can see, this example, you can find many integer instructions, but you can find only 2 floating point instructions. And then also, you can also apply the loop unrolling for this case. And then, if we apply the loop unrolling, we can use more load instructions, but those instructions should be handled by integer pipelines. Also, then also we can use this integer and floating point pair for this instruction pair. So find another pair. Add I and add that S instructions. So if we apply the loop unrolling, then we can also calculate the speed up by this loop unrolling. Okay. And then the limitation. So I already explained that if we this advantage of the loop unrolling is the register pressure. So which means that compiler needs to assign more registers in the unrolled loop. And then we can find another loop unrolling limitations. And then it is actually it's limitations by some application. So you can in this example. So this is the example of the interloop dependency. So if we see the this loop iterations, then we can find so AI. If we just focus on the AI, so AI use another data from the previous iteration, like I-5. So if we just draw some iteration diagram such as the A0, A1, A2, A3, A4, and A5, then we can know that the A5 is need the data from the loop A0. Okay, so which means that, so actually in the previous example, we assumed that the loop unrolling can be applied to the independent loop. So which means that there we cannot find any dependencies between iteration loops. So it's a very good case. Okay, it's a very good case because so which means that A0, A1, A2, A3, A4, and A5. Here, so actually, we cannot find any dependencies between loops. So which means actually we can execute different loops in parallel because we cannot find any dependency. So which means we can execute the A0 and then we can execute the A1 concurrently and and so on. So it's good for the parallel processing also. It's also good for the loop unrolling. But the problem with this example is that the A5 requires the data from the A0, so which means that A5 cannot be executed before A0 is completed. So actually, if we just apply the loop unrolling for this case, we can unroll the loop up to 5 times because of the data loop dependencies. Okay. So that is another limitation of the loop unrolling. We cannot apply the loop unrolling infinitely, actually. Also, actually, I don't like this kind of code because actually the modern processors, you know, the GPUs are very popular because we can apply, we can execute the parallel processing or parallel applications in GPUs. But if some algorithm use these dependencies, then it's very hard. It's very hard to apply parallel processing in the GPU architecture. So which means that if the loops are independent, like this form, like A0, A1, A2, blah, 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 A100, and then each loop is independent of each other, then we can apply parallel processing very easily. But for in this case, it's very hard. The loop dependencies actually it's not good for the parallel processing. So as I explained, also architectural resistance, because due to the register renaming, then also the code size is increased. So what is the benefit of the loop? So we can write the smaller lines of code, and then well, this is compiled. So it's automatically compiled by compiler. But after loop unrolling is applied, the size of code can be increased because more instructions are generated after compilation. So it is consumed the cache, instruction cache, or memory. The code size can be increased. Our human code size is the same, but loop unrolling is applied. The code size of the compilation can be increased. So another problem is that, so actually we just showed a very simple case, so which means the compilers can estimate the number of iterations in this iterative loop. But you know, if we use the while loop, then the condition of the while loop is determined by the value of the variable. So actually, it's very hard to estimate the number of iterations for this case. So actually, we can apply the loop unrolling for the specific cases. Okay? That is those are limitations of loop unrolling. Okay, and then let's summarize the static pipelines. So we can say about the discuss strengths and the pros and cons of static pipeline architecture. So what are the strengths of static pipeline? So the hardware does not consider about the order of instructions. The hardware static pipeline processor can execute instructions in order. So the hardware does not consider about the reordering of the instructions, which means the hardware is very simple. So it's good for if the hardware structure is simple, and this hardware will consume less power. So it's also it's good for some manufacturing cost. So we can reduce the manufacturing cost, and so we can make the very smaller hardware, and then this hardware may consume less power, not less energy, less power. Okay. So very predictable. Because the hardware architecture is very simple, then we can predict some operations. So operation of the hardware can estimate that easily. It's more relatively easily, not easily, relatively easily. Okay? The performance predictions are reliable. And then so because we can easily estimate some instruction orders, and then some performance bottlenecks in this static pipeline architecture. And then actually the compiler needs to do some many works. So, but because the hardware is very simple, and software engineers or compiler engineers can understand the hardware aspect more easily. Okay, so we can apply to some compiler we can apply the compiler optimization more easily. So I said more relatively easily. Okay, so compilers can have some good aspect this hardware architecture. Power, it's good for the power consumption, but it may not be good for the energy. Okay, it's good for the power. So why? Why we cannot say this static pipeline architecture is good for the energy consumption? Because energy, we need to know, it's very good. It's very important. Energy is the power multiplied by delay. So we can improve the power consumption, which means that we can reduce power consumption with a very simple hardware. But if the delay is increased, then energy consumption can be also increased. So actually, if we just consider the workload in our computer system, we need to consider the energy. Okay. Okay. And then power is actually related to the manufacturing cost or cooling cost. Okay. And the weakness. So when I explain about the static pipeline architecture, I assume that every memory access is hid in the cache. It means that the load instruction or store instruction consume only one cycle. But it's not true, It's not true for the real cases. So actually, it's very hard. It's very hard to handle the cache miss cases with the static pipeline architecture. Also, it's not good for the compiler. So actually, compilers cannot estimate the exact required cycles for cache misses. The memory hierarchy is also a little bit complex. And it's very hard. it's very hard to estimate those required cycles for fetching instructions or for fetching data from the memory. Okay, so no mechanism to handle cache misses. It's very critical actually. And then also the dynamic information is not used in this static pipeline architecture. And then another issue is the precise exceptions. So if we apply the out-of-order completion architecture, then we cannot. It's very hard. It's very hard to apply precise exceptions. Okay, and then burdens are moved to compilers. So other architecture is relatively simple, so which means that we can reduce the hardware complexity of this static pipeline architecture. But in order to increase the performance, we need to apply some compiler techniques in the static pipeline architecture, and which means the compiler compiler structure can be more complex. Okay? So which means that the burden of the it's very, very interesting. So our computer system is composed of software and hardware, and then the burden of the performance benefit can be given to the hardware or software. So which means that if the hardware structure is very simple, then the burden is given to the software, is moved to the software. And we need to design more complex software, so we need to apply more fancy optimization algorithm in the software. So this is the kind of GPU application. So the GPU hardware is relatively simple compared to our CPU core, which means that not to increase the performance, then we need to write the very fancy code and very fancy software. So okay, then if the hardware is complex, if hardware can dynamically schedule instructions, and hardware can handle some data header efficiently, then we can reduce the burden of the software. Okay? It's kind of 폭탄 This is 그 리얼 월드에서 폭탄 걸리기라고 하죠. 그거 비슷한 거. Okay, I'll conclude the static pipeline architecture and then let's move on. Dynamically scheduled pipeline. So actually, we can simply call this process architecture is the out-of-order processor architecture. It's very important because the modern processors now employ most of the modern processors employ out-of-order processor architecture. Okay, like Intel CPUs or AMD CPUs, or even the ARM CPUs now employ out-of-order processor architecture. Okay, so in this out-of-order processor architecture topics, we will learn about these topics like Tomasulo algorithm and then dynamic branch prediction. It's also very critical for the performance, and then it's very important. Speculative execution and then register renaming. So those are some highlight of the modern process architecture, like out-of-order process architecture. So it's very good it's very critical for the performance. Actually, the speculative execution. Also, we learn about the register renaming, and then those are some additional techniques that can increase the performance of out-of-order process, like speculative scheduling, and then superscalar, multiple instructions per clock. It's a superscalar architecture, the value prediction. It's a more aggressive prediction technique, like value prediction. So it was explored in the old generation. And so, okay, so you can apply the same very aggressive prediction to data. Okay, let's start from the Tomasulo algorithm. So let's start from this statically scheduled process architecture. So actually, this is, if you see this process architecture, then we can find that, oh, this is the out of order completion architecture. So it is the out of order completion. So in this architecture, so we can find that, as I explained, the latency of the floating point units is lower than the latency of the integer unit. But in this process architecture, so we can find that there are multiple execution engines. Then how can we reorganize this process architecture? So it's so problems that low latency. So in this architecture, we can find that the execution engine, the execution units have exhibit various delays. So which means that it calls out of order completion. And how can we reorganize this process architecture? Which means that there are multiple engines, then instruction can be fetched, and then also another problem is that multiple execution engines have various delays. And how can we handle this case easily with the process architecture, like a hardware architecture? Okay. So also another challenge is that with the statically pipeline architecture, we cannot find any available instructions because of data dependencies. Also another word is the branch instructions. So because of the branch instructions and then data dependencies, it is very hard. It's very hard to find the available instructions. So that is another issue. But in order to increase the performance of the processor, we need to increase the parallelism. It's the baseline of the processor architecture. We need to increase the parallelism. So which means we need to increase, so kind of, so for the aspect of the instruction, we need to increase the instruction level parallelism. So if we just focus on the thread level, then we need to increase the thread level parallelism. But main fundamental basis is that not to increase the performance, we need to increase parallelism. Okay, that's very important. Now, how can we increase the parallelism? So how can we increase the instruction level parallelism? We just focus on the single thread, the performance of a single thread in this case. So how can we increase the performance? So first, we need to find as many as available instructions. How? Actually, we already know that the code size is very large, so which means that our single thread already includes the many instructions. So there are many instructions in our code, but actually, in the processor, it's not find any available instructions. Then, as I explained, it's because of data dependencies and then branching instructions. And how can we increase the available instructions? So that's the start point of the out of order execution engine. So what is the problem of the static pipeline architecture? The problem is that if we just add x1 and add x2, the problem is that if this so there are two instructions like add x1 and then load x1. So sorry. I'm sorry. Add x1 and sub x2. The problem is that the static pipeline architecture, so we cannot find any data dependency between this add instruction and sub instruction. But the problem is that if add is blocked, it's stored, so which means it's stored in pipelines, then even though sub instruction can be executed in the processor, which means that the operands, the required operands for the sub instructions are ready, so which means that this instruction can be executed. But because of the static pipeline architecture, these sub instructions cannot be executed. Okay? That's the problem. But we already know that if the operands are ready in the processor, then we can execute the sub instruction. That is the starting point of the out of order processor architecture. But if we apply the out of order execution, so which means that even though this order of the instructions are reordered, then the final result should be correct. So which means we need to consider the additional data hazard. Actually, in the out of order compilation engine, then we need to consider also the wow hazard, but in the out of order execution architecture, then we need to also consider the wow WAR war hazard. So right after read hazard. So we need to consider these different kind of hazard. So actually in this slide, I just showed the examples of row register or the hazard for registers, hazard in registers, but we need to consider the data hazard in memory. Okay. So it is because and I explained about the process architecture and the result. The final result by instruction is to change the data in register file and memory. Okay, so which means that when the instructions are executed in order, so in a program, in a code, programmers assume that instructions are executed in order, and then instructions are executed atomically. So which means that the result of the instructions are reflected immediately. So it's the main concept of our code. It's very important. The programmers assume that instructions are executed in order, and then instructions are executed atomically. But it's not true in our processor, the hardware processor. So actually, so it's very easy. So starting point of the out of order execution engine is that if the operand of a certain instruction is ready, then you can execute these instructions. That is the starting point. But the first assumption is broken. The programmers, the software views that the instructions are executed in order, but in a processor, this assumption is broken. Okay, that's why the out-of-order processor is. Then how can we provide this in order execution, the in order execution assumption by software engineers, the software programmers. So now to support the first, the software assume that the instructions are executed in order. So which means the hardware, even though we apply the out of order of the execution engine, then hardware also need to provide this support this assumption. But how? In order to support this assumption, we need to consider the data hedge. Okay, we need to consider the hardware needs to consider data actually dependencies between read and write in registers and memory. It's very important. This is a critical challenge of out of order execution engine. So we need to consider three types of data hazard: null hazard, wrong hazard, and war hazard. The read at the right, write at the right, then write at read hazard. We don't need to consider the raw read at the read because read does not change any data. But problem is that store change data in register file and the memory. That's why store instructions and then the arithmetic instructions which change any instruction changes data in the register file actually. So the instructions they can change the values, the data in register file or memory are very critical. So in order to support this assumption, the hardware needs to consider data dependency regarding low hazard, war hazard, or low hazard, war hazard, and wow hazard. And you can find the W, 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 and W, and W. Okay. So please, so it's very important. Please remember that store instructions. So if the data is changed by instruction, these instructions are very critical. So that's why do I explain? Emphasize this. It's the basic of hardware architecture. It's the basic of memory architecture. Read is very simple. We don't need to consider about the read because read does not change any data inside of the register file and memory, but write is very critical. We need to handle the write very carefully in a hardware architecture because write can change the data. It's always very important for the memory coherency or memory consistency. That's why the write is very important in the computer architecture. So you need to consider these three types of hazard and the low hazard. And low hazard is relatively simple, and it is actually the low hazard is called the true data dependency. Reason because low hazard is very simple and obvious. So which means that if the operands are not if this result is not written by formal instructions, then the following instructions cannot use this data. It's very obvious and simple. It's a true data dependency. Actually, so in the programmer's perspective, and we programmer just consider this low hazard, right? Because when you write a program, so we assume that like A equal 1, then B equal A plus C. So we assume that A is updated immediately, and the following instructions, following statement, use the value of A immediately. So that's why the low hazard is called the true data dependency. And then actually the low hazard can be supported easily by the statically pipeline architecture also. So low hazard is obvious and it's very simple. Well, how about the war hazard? Actually, the programmers does not consider about these cases like war hazard and then wow hazard. So what's the problem? So let's see this war hazard. So we did by this formal add instruction. The add instruction need to read data from register R3, but the next add instruction, try to write data to the R3. And then we can simply imagine like this. This is the out of order execution processor. So which means that even though this is the instruction order, so this regardless of the instruction order, this add instruction, the future add instruction can be executed early. So which means R3 can be updated by future value, and then if this add instruction is executed later, then add instruction may use the data generated by this future add instruction. And then actually the program, the software does not consider these cases because as I explained, software programmers think that every instruction is atomic, and every instruction has the instructions are executed in order. But if we just apply the out of order execution, then it consider this case. So which means that the future instructions can be executed earlier. So we need to consider this war hazard and then wow hazard. So it's also saying you can easily see some problems by wow hazard. So same registers are trying to be written by two different instructions, which means that the future instructions can be executed early. So what's the problem? So we assume that when these instructions are executed, then we assume that the R2 has the result of R1 plus R3. But because when the execution order is reordered, then R2 may have the R5 plus R3 after these instructions. So we need to also maintain the order of data write. Okay, so and then it's same to the memory. Okay, it's the same to the memory. So what can we find here? So we can apply the load and store instruction for this case, like low hazard, war hazard, and wow hazard. So load and store. If we just consider the low hazard for memory, then which means that we need to maintain the store and load instruction, the order of store and load instruction for the same address. For the same address. So store and load instructions should be maintained. And then if we just consider the war hazard, then which means that we need to consider the load to store order. Okay. So it's for the same address, actually. So this order should be maintained inside of the process. And how about the wow? Store to store order should be maintained. Okay. So if we apply the data handler cases for the memory, these orders should be maintained. But it's not very critical. It's very critical for the computer architecture. Storage is very critical. So this order should be maintained. Okay. This is the another challenge of the out of order execution. Okay. I already explained about the memory. So low hazard and wow hazard and war hazard should be considered for memory and registers. It's very important. So it is because of software's assumption. Data dependence will be maintained, but instructions can be executed out of order. But even though the instructions are executed out of order, and we need to maintain the data dependencies. Also, another challenge is the branches. The issues in the branch instruction is that we don't know which instructions can be executed. Which instructions can be fetched from the instruction memory. So actually, when the branch instruction is executed, then the code, the path of the code execution can look like this. So there can be many branches from the code execution path. But this execution of the code is dynamically determined during the execution of the thread. So that is the very difficult part of the branch. Okay. The problem is that if we can know the exact path of our program, then we can select the more instruction from this path. So which means, if the program execution path is only one, so which means that we can pick many instructions from this path. But because of the branch, we don't know which path will be executed. So cannot pick many instructions in this path. That is another challenge of the out of order processor. And also precise exception. The challenge of the out of order execution is sent to the out of order compilation engine, our out of order compilation architecture. So we assume that our processor supports the precise exception, but with the out of order execution, it's very hard to support the precise exception because the compilation of the execution is also out of order in the out of order process engine. So this is another challenge. Okay. So let's take a break for 10 minutes. Okay. So now it is 11:37. So I will resume the class at 11:47. Okay. So let's take a break for 10 minutes. And I posted the first homework assignment on the Blackboard. So for this assignment, you are requested to run spec benchmark suite. Then if you run the spec benchmarks, then you can measure the execution time, and also you can compute the spec score. Okay, and then so actually I made a Docker file, so you can easily build your Docker image using this Docker file. Okay. So if you build this Docker image with this Docker file, then you can actually the spec benchmark suite is automatically downloaded on the Docker image, and then also it's automatically installed. So it is very convenient. Okay. But if you are not familiar with how to use Docker, and you can actually in this document I do not explain about how to use Docker. Okay, so you can visit this Docker website. Okay, and then you can actually it's easy. Okay, so you can build Docker image and then you can run the Docker image, and then you can also execute the bash shell using this Docker command. Okay. So you can install the Docker engine on your Windows or Linux operating system. So I recommend to use the Linux operating system because you are taking the computer architecture course. So it's good to use the Linux operating system for this case. But anyway, you can install Docker engines on Windows or Linux operating system, and then using this Docker file. Okay, so you can find the Docker file here on the. So this is the first homework assignment, and you can download the file from here. And so, and then you need to answer questions in the what to do section here. And you can submit your homework report via Blackboard. Okay. So this is just actually your task is to run a spec benchmark and then compute the spec score by running this spec benchmark on your machine, on your own machine. Okay, so benchmark score will be different for the different machine. That's fine. But so you need to specify the some hardware specifications of your computer system first, and then you can easily measure the execution time using the spec command. So you can easily compute the spec scores. So you can change some compiler optimization level. Then you can also change the number of threads and the spec benchmark. You can compare the performance by this compile optimization levels and then number of threads. Okay, but it may take time because you just run the benchmark. Actually, I just select some very short benchmarks, so the small benchmarks, which means that the execution time is relatively short compared to the other benchmarks. But please start early. It may take time to run several benchmarks several times. Okay, I think the 2 weeks is enough for doing this homework. But please start earlier. Also, if you are not familiar with the Docker, then you can visit this site, the Docker site. Okay. Also, another announcement is that for the upcoming 2 classes, I will provide only the online classes because for 2 weeks it's midterm. It's a midterm period for 2 weeks, so we cannot use this classroom. So I will provide only online classes for the upcoming 2 classes. Okay. Any question about the homework? Okay, let's resume. Okay, and then let's see how can we organize the out-of-order processor architecture. So you can start from the simple pipeline architecture, which means the simple 5-stage static pipeline architecture. So I believe everyone knows that simple 5-stage pipeline architecture is composed of 5 steps, 5 pipeline stages. So it's instruction fetch, instruction decoding, execution, memory, and write back. And then in the previous out-of-order compilation architecture, then we already learned that you can separate the integer engine and floating point engines, like integer pass, integer execution pass, and then floating point execution pass. But actually, for the memory instructions, so actually we require this additional memory stage for only memory instructions, like load and store instructions. Well, which means that we can separate this memory access path, so memory instruction path also. So we can reorganize the static pipeline architecture like this. So this is the instruction fetch stage, and then it's the same with the piece program counter, then we can access the instruction cache, and then the instruction is fetched from the instruction cache. And then this is the decoder stage, instruction decoding stage. So, and then it's the same to the this architecture like here. So there are different kinds of instructions like integer type instructions and the floating point instructions. And then, the most of the processor separate the instruction integer type registers and then floating point type registers. Okay. So in this architecture, we also separate the integer type register file and then floating point register file. And then actually the fetched instructions are decoded by instruction decoder. And then based on the this decoding result, then we can separate the integer type instructions and then floating point type instructions. These integer type instructions include integer arithmetic, also memory, load store, and branch instructions. Okay, and the floating point instructions include only floating point arithmetic instructions like add.s, add.d, or multiply.s or multiply.d. So, which also I already mentioned that we can separate the memory paths and then integer arithmetic instruction paths. So which means that we can separate the memory paths like here. Actually, for the memory paths, we first need to generate the address for memory instructions, like load and store instruction. So actually in the static pipeline architecture, we use the integer ALU for computing addresses of memory instructions. But we can use the another separate address generation unit here, just adder, it's very simple. So it's not critical for the hardware resources. So this is the memory path. So which means that in the execution stage, we can have integer type execution, integer unit, and then memory unit like load store unit. And the load store unit includes the address generation unit, AGU. And then also we can use the floating point unit, FPU here. And then, if we use the integer unit or floating point unit, then we don't need to access memory, so like actually the data cache, which means that if the execution is completed, the result it can be written back to the register file here. So which means that we can make the write back pass here. So it's a write back pass, is a write back pass. But the memory type instruction is a little bit different. The memory type instructions need to access data cache, so we require another stage, pipeline stage that can access the data cache here. So after the data cache is accessed, then the result can be also written back to the integer type register file and or floating point type register file. It depends on the load, the integer type load or load.s or load.p. So it's a floating point type load instruction. So this figure just shows the reorganized static pipeline architecture. Okay? And then this type of architecture can be also is applied to the our commodity architecture, such as the ARM processors, pipeline processors. Okay. And so what can you find? We have multiple processing engines for integer and then memory instructions and floating point instructions. Then which means that the instructions can be executed in parallel for these different type of processing units. Also, the integer type register file and floating point type register files are separated. Okay, so we can design the processor like this. But problem is that actually the integer type unit integer type processing engine is relatively simple. It's actually very simple. So we can assume that so integer type ALU consume only fixed cycles, like one cycle. It's very simple. How about the floating point ALU? So we already know that the floating point unit consume more cycles, like 5 cycles, but it depends on those instructions. Like you can apply the multiplier. It's very similar for the add, sub, and multiply, divide for the floating point unit. It can have the fixed cycles, but if the number of cycles is larger than the integer type processing unit. Also, the processor can support some special functions like the square root, but we just ignore this case. We just consider the floating point instructions here. Oops. Right. Okay, and then but the problem is memory. So actually, we assume that the memory. So we just assume the cache hit case because so we can assume that the memory has the fixed latency, fixed cycles, but it's not true actually in the real world. So because based on the hit or miss of this data in the data cache, the memory instructions may have various latency, which means that the required cycles for the memory instruction vary by situations. So this memory instruction can take a longer time or can take only one cycle in this case. So what can you find? What can you observe in this case? So there are multiple processing engines, but these processing engines have various delays. Okay, you cannot use the fixed cycles. You cannot apply the fixed cycles for these processing engines. Then, what should we do? The problem is that also we need to also consider some branch instructions. Also, we need to consider the cache miss hit in this instruction cache. So what I want to say is that every processing engine or every stage may have various cycles. It means various delays. Okay, and then hardware cannot support. Actually, these processing engines have fixed delays or fixed cycles, and we can make very simple hardware because we can control the flow of the instructions and then some timing of the processing. But problem is that the quite stages and then hardware engines can have various delays. So how can we solve this case? How can we handle this case actually in hardware? It's like this. I will use this slide. So there is a producer and then there is a consumer. So this consumer consumes the result from producer. Okay. Which means that the consumer receives the result output from this producer, and also consumer makes some result. Okay, but the latency of this consumer can vary like this. So we may know the average latency of this consumer, but in the real world, the delays of this consumer can vary. So which means that the task can be processed very quickly. Also, task can be processed with very long more cycles. They require more cycles. So how can you handle this case? But we already know we know the some average latency of this consumer. And producer will generate some result here. And producer delivers the output to the consumer. How can you solve this case? It's also very important for real world. So there is a producer and then there is a consumer, and then actually it's a sender. We can say that this is a sender and then this is a receiver, and then the receiver processes so senders the result with the various delays. How can we solve this case? In hardware, in the real world. We can solve this problem with Q. Okay? And then we can solve this problem in the real world with the storage. Okay? So the result from the output from this processor can be temporarily stored in this Q, temporary storage space. Then consumer can execute make use of the result from the producer. And if there is no Q here, so what will happen? So if there is no Q, let us assume that there is no Q between producer and consumer. And what will happen? Sometimes the consumer will work very fast, but it's good. The result from the producer will be processed quickly. But if the consumer is very slow, then producer is also cannot deliver results to producer cannot deliver results to the consumer. So which means that performance of this producer is degrading. So it's a wasted. Okay? Do you understand? So which means that if the delay is there, delay varies, then we can solve this various delay of the consumer with the Q. Okay. It's very important in the process, in the hardware design. So we can distinguish the producer and consumer, producer part and the consumer part. And if the delays of this consumer part varies, then we need to solve the situation with the queue. And it's the same to the process architecture. Also, it's the same to the our real world situation. So I said the problem is that these processing units may have various delays. Okay, so in this case, how can you solve this case? We can add queues in front of processing engines. Okay. Also, another delay issue is that because of the data dependencies, the instruction can be executed while some instructions cannot be executed by the processing engines. So in order to solve this case, we also require queues. Okay, queues here. So we can make several queues before these processing engines. Also, data cache. Data cache has also various latencies, and we need also queues for data cache accesses. Okay, so why did I draw two queues? It's queues for load. So load queue and then store queue. You can say, this is a queue, this is the as queue. So store queue and then load queue. Okay. So because the data cache has some various latencies, then we can insert queues between this execution pipeline stage and then data cache. Also, we can fetch the instruction in the fixed cycle, actually, but some instructions, so so these are some consuming part of the instruction fetch, and then we already know that this is the processing engines, and the processing engines may have various delays, which means that we need to also require queues between instruction fetch and instruction decoding, because this is the second part. The part has the various delays, so we need additional queue between instruction cache and instruction decoding stage. So actually, in the statically pipeline architecture, so we assume that every processing engines have a fixed delay. So which means that we can easily handle this fixed delay with the statically scheduled pipeline architecture, with a simple pipeline architecture. But we not support the out of order execution, and then also we need to consider some real world problems like various delays in the memory systems. Also, we need to consider some various delays by data dependencies. And then in order to not handle these various delays, we require queues between stages. Pipeline stages also require the queue in front of the processing engines. So we require the queue here, the queue here, the queue here. So in this process architecture, this queue is called the instruction fetch queue, IF queue. And then each queues before the processing engines are called the issue queue. ISS queue is called issue. And then, as I mentioned, these queues are called the load queue and store queue, LQ and SQ. So this process shows the advanced architecture. It is developed from the statically scheduled architecture, and then the processing engines are reorganized, and then because and then you also need to handle some real world problem, so various delays. And so we insert the queues here. And then the out-of-order execution algorithm is called the Tomasulo algorithm. It's developed based on this architecture. Okay. Okay, so I already explained about the here. So this is the architecture of the Tomasulo algorithm. So you know this architecture actually I drew this pipeline dynamically controlled pipeline architecture in the horizontal direction. But you know in the pipe that is Tomasulo algorithm architecture, you can find that this architecture is drawn vertically. So you know you can find the instruction cache here, and then the instructions are fetched by instruction fetch engine, and then fetched instructions are queued in the instruction fetch queue. So this is the instruction fetch queue. Okay, and then so queue is just the instruction fetch queue is just the file form. Okay, so file form means there is the first in, first out. So which means the instructions are fetched in order, and the instructions are decoded in order by instruction decoder. And then the decoded instructions are delivered to the different issue queues. Okay, and then this process is called dispatch. Okay, so called the dispatch. So instructions is decoded, the last instruction. The last instruction is decoded, and then this instruction is dispatched to the different executes based on the instruction class. So the instruction is dispatched to the different instructions, and then in this architecture, if the instruction is ready for execution, so which means that, for example, I can use like the add instruction, add x1, x2, x3. So this add instruction requires the two operands from the register file, the integer register file. So if these operands are ready in the process in this processor, then we can execute this instruction. Okay. So the instruction can be delivered to the processing engine, to the branch, the AGU, and the point. And then this processor is called issue. Okay, so instruction is issued to the processing engine. And the noun form is the issuance. Oh, and then if the instruction, the execution of the instruction is completed, the result is delivered to the common data bus. It's called the CDB. It's a common data bus. So common data bus. Okay, and then the result is written back to the integer registers or floating point registers. Also, you can find the load queue here, store queue here, and you can find the data cache. Okay, so it is the Tomasulo algorithm applied to the out-of-order processor architecture. Then you can say that this out-of-order processor is early out-of-order processor architecture. This early out-of-order processor architecture was developed from the static pipeline architecture. We just include some queues here, and then we separate some instruction execution path, and then the thing is very similar to the static pipeline architecture. Also, this out-of-order processor architecture also performs some required 5 stages. Right? instruction fetch, decoding, execution, memory write back. We support the all required processes, all required steps for executing instructions. Okay. Then how can you support the robot execution? Let's start from how can you? So it's a little bit complex, but I try to explain. Actually, the Tomasulo algorithm, we can say that this is the front end. So front end includes the instruction fetch and instruction decoding, actually dispatch, instruction decoding and the dispatch part. So front end includes the instruction fetch, instruction decoding, and dispatch. And then back end part includes the processing part. So like the issue queue and then processing engines, and so the memory part, and then this common data bus you can call this is the front end and this is the back end. Then the main idea of Tomasulo algorithm means that so instructions are issued in the issue queues of the different classes. Okay, and then which means that if instructions are issued to this issue queue, then we may have to add R1, R2, R3. So for example, this instruction is issued to the dispatched to this an integer type issue queue. Then we can know not to execute this instruction requires two operands, R2 and R3. Okay, so which means if R2 and R3 are ready, so which means the valid data, then this instruction is executed in this by integer unit. So which means there can be some another earlier instructions in this process, like sum and then some multiply before this instruction that this is integer issue queue. But because this add instruction is ready in this is queue, then we can execute the add instruction before any other instructions. That is the main concept of Tomasulo algorithm. Then how can we support this in out of order execution? It's very simple actually. The main concept is that if the data is ready, the operands are ready for this instruction. We can store instructions in these different issue queues, and then if we can find the ready instructions in the different issue queues, these instructions can be executed. Then how can we support this operation? Also, another challenge is that we need to consider the three data hazard, row hazard, word hazard, and then word hazard. And how can we support this case? How can we solve this hazard? Actually, the Tomasulo algorithm solves the data dependency with the tags in issue queue. Okay. So tag means that when the instruction is so like let's start from and R1, R2, R3. So when this instruction is dispatched to the issue queue, then we can know that, oh, this add instruction try to update the data in destination register R1, right? So this add instruction will change the data in R1. Okay. So when this instruction is dispatched, then it will take time until this instruction is executed by integer unit. Before this instruction is executed, R1 is the unknown value. It's unknown. So already dispatched, decoded, and dispatched, but execution of this instruction is completed. We don't know the actual value of this R1. Okay? R1 is unknown. So R1 should be here. R1 is in the register file, but R1 is unknown until this instruction is executed. So in this case, when the add is dispatched to the issue queue has some tag, okay, tag for each entry. This tag is written to the R1, so which means that tag indicates that instruction is dispatched. So instruction is on the way to the execution engine. But until this instruction is completed, we don't know the value of this R1. Okay, so it just when the instruction is dispatched to the vulnerable issue queue, the tag, like the issue queue entry number, is updated to the register. Okay, and then if this tag is valid, then which means that this R1 is being executed, so being updated. It will be updated, but it's not yet fixed. So it's not yet updated, which means that the R1 will be updated in the future. Okay, we don't know. So R1 is returned to this register file, and then also R1 has the tag. So and also this is add R1, R2, R3, and then the following instruction like sub requires the data from the R1, R5, R4. And then sub is dispatched, but this sub instruction check the register file. But we find that this sub instruction check the register file, but when the check register file is checked, then this register has valid 10, which means we need to use the R1, this sub instruction. And we need to use the R1 when it's not ready in this processor, but it has the tag. So this tag is deleted. And this sub instruction is dispatched. This tag information is also delivered along with this sub instructions. Okay, so instead of this R1, sub instruction has some operands like this R4, and then some tag for this R1 and R5. Okay, instead of R1, sub has a specific tag for this R1. Then when the add instruction is executed, then R1 will be calculated, right? R1 will be computed. Then R1 is delivered on the common data bus here. Okay, so the final result and then tag number is delivered to the common data bus. Now, as you can see, common data bus is connected to the so issue queue, every issue queue. Also, the common data bus is connected to the register files. Right? integer and we put the register file. So which means that and the result is generated and then result is delivered via common data bus. Then this tag is checked. Tag is checked in register file and issue queues. So this process is called snooping. Okay, so with the same data bus, the information is delivered via the same common data bus, the same data bus. Then every tags in the issue queues and then register files are checked. It's a snooping. It's a snoop. So if the same tag is found in the issue queue, like so some has the tag number here. Oh, same tag is found. Then this data is delivered to the sub queue, sub instruction in this issue queue. Also, the value is delivered to the register file. Okay, that's how out of order execution is supported by Tomasulo algorithm. So what is the main idea? What is the main idea of the Tomasulo algorithm? It's very similar to the register renaming. So what does that mean? So instead of a real register number like R1, this number is renamed to the tag number of the specific issue queue. Like add instruction, try to update data in R1, this destination register. And then when the add instruction is dispatched, so it's before execution, then this R1 is renamed to the tag number. And then following instructions like sub instruction that requires the data from the R1, then the operand of the sub instruction is also changed to the tag number. It's the same tag number. So which means that when the specific register, and then this specific register will be updated because the instruction, a certain instruction is dispatched. But during this intermediate period, the processor changed the name of this register with the tag number. And then the processor handles the data dependency with this tag number. That is the main idea of Tomasulo algorithm. So, you can solve the low hazard, right? Because between the add R1 and then add add R1 and then solve R1, and then this R1 is changed to the tab, and then actually the data dependencies are checked by this tag number. So we can say, oh, low hazard is solved by this tagging. How about the wow hazard? Like add R1 and then solve R1. So we can solve this wow hazard by renaming the default tag number, right? And the add R1, so this is the formal instruction. This add instruction will be dispatched earlier, okay? Which means that this add instruction, the R1 actually have the tag, like tag 1, so another tag number. And then another sub instruction is dispatched and then try to update data in R1. So in this case, R1 has the default tag number. Okay? So when the register file, then this register file firstly has the tag number 1, and the add instruction is dispatched. But when the serve instruction is dispatched, this tag is updated to the tag 2. It's a default tag number. So which means that when the serve instruction is completed, it completes its execution earlier, then R1 has the value of the serve instruction, not add instruction. Okay? That's how wow hazard is solved. Also, we can say that with the same mechanism, the wow hazard can be also solved. Okay? So it's the Tomasulo algorithm implement the algorithm for the execution with the tagging. So the tag is assigned when the instruction is dispatched, and then this default tag, with this default tag, so we can handle the default header. It's very similar to the register renaming. Okay. So actually, the register renaming is not required for the row header, because row header is the true dependency, data dependency. But in order to solve the wow hazard and the war hazard, then we need to change the register name. Okay. So this is the main idea of the Tomasulo algorithm. And let's see the detailed operation of the Tomasulo algorithm for each stage. The first, let's see the front end part here. So I already explained about the front end instruction fetch and then instruction decoding part of the Tomasulo algorithm. The front end is composed of instruction fetch, instruction decoding plus dispatch. Okay, so instructions are fetched from the instruction cache by instruction fetch engine. Okay, so and then dispatched instruction is queued in the instruction fetch queue. It's called the IFQ. And then in the computer architecture, we frequently use the abbreviation form. So please remember that this abbreviation form of the component name of each component. And then I said that this IFQ is the file 4, and then first in the instructions are in orderly delivered to the instruction decoder here. Then you can find the instruction decoder engine and the instruction dispatch engine here. And then if the instruction is located at the last part of the instruction fetch queue, and this instruction is decoded and then dispatched to the backend part. So like the issue queue. So you need to understand that when the instruction is dispatched, and the tag is inserted to the instruction, tag is inserted, then some some processing and then some mechanism for out-of-order execution is applied. Okay, so when the instruction is dispatched. And then actually the front-end part is relatively simple, right? So it's composed of instruction cache and then instruction fetch, and then IFQ is just the FIFO. And then the instruction is decoded and then dispatched. So it's the front-end part. Then let's see the back-end part. I already explained about the back-end part here. So back-end part is composed of the processing engine here, execution engine use. Also, we can find the different execution engines for the different instruction classes. And then also you can find that issue queue here is queue. Then we can also find the issue engine. Issue queue is not FIFO, right? So in the issue queue, it's not FIFO. It's not FIFO. So it means that by this dispatch engine, instructions are issued to the monomule entry of the issue queue. And then the issue queue is used for supporting out of order execution. So which means that the issue queue is not FIFO. Okay, which means that if the instruction is ready for execution, this instruction can be executed. That's it. Okay, and then also the tag is assigned. Then tag is also here. And then the monomule instruction is ready. This issue queue. Then this instruction is issued to the execution units, like integer branch unit, and then AGU, and then floating point unit. As I mentioned, there is the CDB, it's a common data bus. And then the execution is completed, the result and the tag is delivered via common data bus. Okay? And then also you can find that the data cache is connected to the common data bus. And then also you can find the load queue and the store queue here. And then we require this load queue and the store queue for supporting data hazard in memory. Okay? Like a data dependencies. Like well hazard, the low hazard, well hazard, and more hazard in the memory. Okay. That is the backend. The backend is composed of issue queue, and then issue engine, and then execution units, and then memory, and then common data bus. This is the backend part of the Tomasulo algorithm. And I already explained about this part here, and I hope you can understand how this component works. Component work in the Tomasulo algorithm. Okay, and then I already so let's see how the tag is handled. So data hazards are handled on registers. I already explained here also. So actually the data hazard, I need to consider the three types of hazard: now, while, and then work. And then I explained that the adding this instruction is dispatched and destination register. Destination register, this instruction is changed to the tag, this tag number. Okay. And then which means that while this instruction is being executed in the backend, then we just handle the tag, not the register number. So this is important. And then I already explained that how we can solve the wow hazard and war hazard without this tagging. Okay, you can also simulate the war hazard without this tag. Okay, all right. So then, as I explained, when the instruction is dispatched, the tag is updated to the registers. And then these tags are used for the read, register read for the following instruction. So which means that when the instruction is dispatched, then this instruction checks the status of the registers. So which means that add instruction, add R1, R2, R3. So this add instruction requires two operands from the registers R1, R2, and R3. So which means that when this add instruction is dispatched, The add instruction requires to check the status of R2 and R3. So the add instruction checks the tag is invalid or tag is valid. So what is this case? Tag is invalid. So which means that this is the register R2, but R2 has also tag number, but this tag is invalid. The tag is invalid, which means that this R2 has valid data. Okay, so I forgot to explain about the so at R1, so this is the destination register. When this instruction is dispatched, so R1 is here. So R1 instruction is dispatched. And R1 should be updated by this instruction. So, and then this update is not completed. So we just assign a tag, so tag number, tag 1. When the tag is assigned, this tag is valid. So which means that R1 does not have any valid data. Why? Because this R1 is being executed by some instruction. So it will be updated by dispatched instruction. Okay. So R1 does not have any valid data. This instruction is just dispatched. This instruction is in the processor, so we don't know the actual value of this instruction. So result. So when the tag is valid, this register does not have valid data. It's unknown data. Okay. So vice versa. If the tag is invalid, so it means that this register does not have any tag numbers. It's invalid. So it means that the register has valid data. Okay. It's already updated by other instructions. So okay. So tag is invalid, then this R1 is already updated by formal instructions. So this is the already updated value, valid value. We can find the valid data is in the register, so which means that we can read this instruction. This dispatched instruction can fetch data from read the data from register file. Okay. So dispatched instruction may have different status, and R1, R2, R3. So this dispatched instruction may have tag number, which means that this data is not ready. It's not ready. So then this data is being this data will be calculated by processing engine, but this is not ready. So we cannot find any valid data from register file. But this R3 may have the valid data. So which means that this data can be read from register file. So we cannot find any valid tag for this register file, this register number. So which means register file has valid data. So we can read this data from register file. So when the instruction is dispatched, I said that the operands of the instruction may have different states. Like so it can have tag, then it can have valid data. Okay. And then how can we solve the? And then with the tagging, and we can solve low hazard, low hazard, and low hazard. Then how about the memory? I said that we need to also consider the 3 types of data hazard on memory. But as I mentioned the 3 data hazard, then we need to check the address, right? So data dependencies should be maintained for the same address. That if the address is different, then it means that these are different data. Okay. Then what's the problem? Actually, the register is relatively easy. So checking the data hazard on register is relatively easy because the number of registers is just 10. So about is about 10 some tens of registers. There are tens of registers. So we can just check the register number like 0 to 31, and that's it. But otherwise, if you want to check the address of the memory instruction, so what is the size of address actually? The size of the address is the same to the virtual size of the virtual memory address. Well, so in the commodity CPUs, the size of the virtual memory address is the only 8-bit, which means we need to distinguish the 2 to 48 different addresses for the memory space. It's not easy. Actually, the register number is the determinist value, which means that the register numbers are included in the instructions. So we can easily know, we can easily recognize the register number. So which means that we can easily check the data hazard on register. But address, the address is determined by register value. And then, the register address, we may have the 2 to 48 different addresses. So checking the same address it's also challenging. It's not easy. But we need to also check data hazard on memory. If not, then this processor may generate the incorrect result. We need to avoid this case. So actually, we need to check the address of load or store instructions for checking data hazard on memory. Okay. But I mentioned that actually load is okay because the load does not change any data on memory, but store is critical. Store changes the data on memory, so we need to focus on the store instruction actually. So when I mentioned explain about the 3 data hazard on memory, so I know while and were, and I also explain about the order of the load store and store and store load. So actually the store is important. So the first we need to know the address of store instruction as quickly as possible. Okay. So actually the Tomasulo algorithm, the store instruction is split into 2 different instructions. So one instruction is for generating address. Another instruction is for fetching data on register. Okay. So we split the store instruction into store address. So it is used for calculating address of the store instruction, also store data. actually it read data from the register file. Okay. Stores are split into two sub-instructions. Okay. Right. We need to know the address of store instruction as quickly as possible. Also, as I mentioned, there are two queues, load queues and the store queues. And then these two load queues and the store queues track some order of load and store instructions. Okay. And so then we need to track some order of load and store instruction for handling data hazard on memory. Okay. Yeah. I said that store instruction is very critical because we need to check the address of load and store instruction. Okay. And then I already mentioned that the store instruction is split into two sub instructions, like address part and data part. And then what will happen if we still do not know about the store address? So which means that the store address is not computed yet in the processor, but the store instruction is dispatched to the store queue. So this is this case. This is the store instruction, but we don't know the address of the store instruction. Okay, and then there is a load. So and then fortunately we know the addresses of the following load instructions. So this is the order of memory instructions. What should we do in this case? We don't know the address of the store instruction, but there are three load instructions following. There are three following load instructions. We know the address. What should we do? In this case, this load instruction cannot access data cache. Why? So it's very conservative. With a very high probability, address of this store instruction will be different from the addresses of following load instruction. But with a very small, very low probability, the address can be the same to the one of these load addresses. So when the store instruction, the address of store instruction is unknown, then the following load instruction cannot be executed. It's a very conservative approach. But we need to follow this approach because with a very low probability, the address of the store instruction may be same to the address of the following load instruction. Okay, so in this case, if the load instruction access the data cache earlier than the store instruction, then load instruction may have incorrect data. In this case, the load instruction cannot be executed. Another example is the store, store, then store A. It's the same. Actually, this is a very ridiculous case. It's like a store A and store A, the same. The different store instruction try to store the data to the same address consequently. But if we don't know the address of this former store instruction, this store instruction cannot be executed. right, with a very low probability, the address of the storage instruction can be A, and if so, the memory will have incorrect data. So store instruction mirrors. Store instructions mirror in the out of the process architecture also. So because of this feature. So firstly we apply the very conservative approach. So which means that the address of the store instruction is unknown. The following store instructions or load instructions cannot be executed. And then as I explained, in order to handle the 3 data hazard on the memory, the order of the load store and then store and store load should be also maintained. It's very important. And in order to support this data hazard handling, Tomasulo algorithm has the load store queues, and then with this load store queues, the order of the data accesses to the main memory, so it's a memory are maintained. Okay. So I think I need to stop here. Yeah, I will stop here, and then sometimes Tomasulo algorithm may be a little bit tricky for some students, so try to read this slide and try to understand how to handle the data hazard on registers on memory on the Tomasulo algorithm. Okay, so it's very important attention. Okay, so I will stop here, and then I will provide online classes only for the coming 2 classes. Any questions? 네.
버커라는 프로그램을 아직 써보지 않았는데요.
네.
혹시 뭐 이게 영문 설명서 같은 건가요?
버커는 요새 많이 써서 사실 그냥 한국어로 설명된 것도 많이 있고요. 블로그나 이런 것도 찾아보면 많이 있습니다. 그러면 설명대로 별로 안 써도 되긴 하는데 그냥 리눅스에서 돌려도 되긴 하는데 그 설명을 다 쓰는 게 그것도 막 다 찾아가야 되거든요. 그래서 사실은 이렇게 닷컴 파일을 제공을 하면은 다 스크립트가 돼 있어서 그냥 자동으로 다 이렇게 돼 있거든요. 그래서 한 건데 그것도 어렵진 않아요. 닷컴 파일을 깔고 그다음에 돌리면 돼요. 그래서 그 설명된 거는 굉장히 또 많기 때문에 그리고 뭐 닷컴 정도는 좀 알아두시는 게 나중에 뭐 연구나 일할 때 굉장히 편하게 쓸 수 있을 겁니다.